Hey, my name is Paul Jordan, and I'm going to be presenting my multilinear regression project. It's about predictions for birth weight. I chose this topic because my wife and I are expecting our second child, and we want to use this model to help to make a prediction of what our second child's birth weight will be. It's an important indicator for the overall health of a baby, and it can be used possibly as a screening tool to see for high-risk uh, pregnancies. So this analysis builds on my linear regression project using which focused on just term for birth weight, and then we'll be adding extra factors as well. So the data set that I use is from the National Center for Health Statistics for live births in the United States. It's taken from 2014. I chose this because it's before COVID, and basically it had thousands or millions of data points. It was filtered down to a random selection of 1,000 observations. I then eliminated all the female because we know the gender of the baby is going to be male for my purposes. And then I removed any data that was incomplete. And then we looked at these different variables as possible predictive variables. The response variable is obviously birth weight, and that's what we're trying to determine. So the potential predictors were mother's age, pregnancy term, mother's weight gain throughout the pregnancy, prenatal medical appointments, and smoking. The first one I looked at was the mother's age. It was determined that it's not a very large factor. Um, and another one that was not a factor and is very flat, didn't have an influence, was the number of prenatal medical appointments. We thought that this might be an indicator of people that tend to go to the hospital might be healthier, but it turned out it wasn't much of a factor. So the ones that were factors were maternal weight gain, which makes sense. It had uh, a slight positive increase along it, and the term was the strongest factor, which is clearly indicated to have a positive influence, which makes sense. The longer the term is, the longer the baby has a chance to grow. The other one that I selected was a binary variable of smoking status of non-smoking versus smoking. And basically, there's about a half a pound difference between the average in the data set, and you can see it more on the graph showing that versus term, seeing the difference between the two. So clearly there's something there to investigate. All right, so next we did a matrix scatter plot that was used as a visual tool to determine relationships between the response variables. So basically what we found was you can see that the smoking is a binary term that's either 1 or 0, and it seems to have an influence, as well as there's definitely the positive influence of the birth weight, which may have a connection, obviously shows for the term, and possibly one with the weight gain as well, being correlated. The data tend to be clustered in some areas, and you can kind of tell that there's definitely some potential outliers, especially in preterm, being an outlier that had lower birth weights. So we're going to use this to investigate that further. So the pairwise correlations align with what we saw visually on the scatter plot matrix. Gestational term is the strongest predictor of birth weight. Smoking status had a weak but a negative association with birth weight, and that kind of confirms some of the clusters that we saw uh, in the matrix. And then maternal weight gain showed a weak but slightly positive relationship with birth weight. So this indicates, based on the data shown that we ran, indicates negligible collinearity among predictors, which is favorable, and just confirms that term is the strongest influence. So the data set does not appear to have any complications to continue forward with the multilinear regression, since we didn't see multicollinearity, was not apparent. All the values for R were weak, so there seems to be a correlation between term and weight gain at those lower R values, and there indicates that we might have stable coefficient estimates. So a potential issue might be because of the outliers that we talked about before for preterm births, and those are at 35 weeks or below, which might shift some of the slopes. Some of the other things that we might want to look at for outliers might be weight gain that was extremely low, as in like 1 or 2 pounds of weight gain versus the average around 30, and extremely high weight gain that was like 80 pounds or more. So next, we went ahead and made the model using those parameters. So the fitted model is highly significant model with an R-squared value of 0.297. This means that the three predictors together explain nearly 30% of the total variation in birth weight. This is kind of to be expected since there's a ton of environmental factors and genetic diversity among different patients. But it is significant enough to possibly be used as a screening tool. So the intercept is a negative number. This is impossible biologically, but it's still statistically significant, and it's necessary for the linear equation to be fitted correctly. The three predictors are also statistically significant, with smoking having about a 0.318 pounds lighter on the binary of 1 or 0, determining the birth weight. The term basically a quarter of a pound for each additional week, holding other things constant. And then weight gain is only about 0.01 pounds per pound of weight gained, which would be equivalent, over 30 weeks of just about a little over a quarter pound for just a normal birth, quarter pound, half pound. So the root in SE was 1.07 pounds. So there's about a 1 pound variation. For linearity, we assumed that the birth weight has a linear and constant relationship with the predicted variable term and maternal weight gain versus the smoking status, it's just being a vertical shift in the model. Here are some of the diagnostics from the model. So you can see that the error variance or constant variance assumes the spread of the residuals should be roughly the same, and it's a fairly random pattern. Also, the residuals were, in that linear line as well, and the histogram kind of shows that the data set is, fairly evenly distributed around the average, equally on the left and right sides. So next, we took a look at the partial plots in order to determine if there was any visual depictions of interaction terms between the different parameters. So the plots show kind of a random scatter plot around the trend line for most of the plots. The trend lines also have a neutral or mild slope. This indicates the effects of, the term length on birth weight is not very dependent on how much weight the mother gained, and the smoking status was generally negative across everything. The only thing that kind of stood out was that maternal weight gain might benefit, might be interacting with term, and that's shown by the term underscore WG for that weight gain. So that's one thing that we wanted to take a look at further. Here's a table showing the interaction terms. So, and as well as a graph to plot the residuals versus the fitted values for the full interaction model to include all the interactions. So even though the model now has 7 parameters instead of 4, the residual plots look virtually identical to the original model. There's no curvature or pattern, funnel shape, or anything like that. And the root MSE is still around just 1 pound. So the plot kind of confirms that adding all the interaction terms did not add anything particularly useful. And so the simplest and most appropriate model still remains to be the original preliminary multilinear model. Next, we looked at a model search to see if backwards elimination with full interaction model or forward step regression at alpha is at point 1 would arrive at the same original model or improve upon it. So basically what we did first was do the backward elimination. So it had 6 predictors with all the two-way interactions. So the first one that eliminated was the least significant term, which was the effect of smoking. Then it was smoking times weight gain interaction, and then the maternal weight gain itself. So it didn't actually improve on the model, and it had an almost identical R-squared value of 0.294. And so it kind of doesn't add anything. And using the predictor of term times weight gain, and smoking times turn don't really have a practical value, and it'd be hard to actually take that data from a patient for screening purposes. The same conclusion was arrived using the stepwise regression procedure, which was used using the program to best explain the variation in birth weight. So it started by entering the term as the strongest single predictor, then entering term times weight gain interaction, then entering smoking status, and this procedure declared all remaining variables significant. So what it left us was just smoking, term, and then term times weight gain. So just like in the other model search, it did not substantially improve the model with the R-squared value being almost identical. And also, one thing to point out was that the predictor coefficient for term times weight gain was 0.00028. So this equates to about 2.5 drops of water for this term. So that would be the term. So each week times the weight gain of a pound equals 2.5 drops of water. So over a 39-week term, that would mean that you'd only get about 1 teaspoon of water and weight of actual addition to the model, which is basically nothing. So that variable doesn't do much and is not an improvement upon the original model. So the final selected model was the original model, and this is because it met all of the multilinear regressions, and linearity was adequate based on the residual and fitted and partial residual plots, and they didn't show any curvature. Error variance was well supported with the residual versus fitted and scaled location plots. And the modified Levene test resulted in a P of greater than 0.09 overall. So normality of the residuals was also confirmed by the plots, and we checked for outliers as well. Multicollinearity was also negligible, with all the VIFs being at 0.01 to 1.03, so very, very small. So although the automated procedures of backward elimination stepwise regressions provided similar models, they provided weak interaction terms with that coefficient being so small, and the R-squared values were almost identical to the original models. So one of the most important parts of this particular project was for me to actually make a prediction using observational data from the current pregnancy, with our due date being next week. So using the values of today, the time of recording, the predicted value using the model was 7.67 pounds, which is very similar to the average weight of 7.5, which is the national average. So with a 95% confidence interval, so 95% of babies with the same values will be born between 7.5 and 7.8 pounds. And for the prediction interval, we can expect that for one observation, or what we're predicting, it would be between 5.5 and 9.8 pounds. So pretty wide range. But the important thing to note is we're 95% confident that it'll be above 5.5 pounds, which is kind of the cutoff for low weight babies that are higher risk, which is important for us to know to make good decisions with our birthing plan. So the model's usefulness was demonstrated by predicting real world observation for our own family. And some of the things I want to discuss were some of the limitations of the model. So we're only using 3 variables, and there's a huge variation of patients and that were not accounted for. So some of those things that we might look at is the height of the mother, that could be an influence, different genetic influences. Socioeconomic status is a lot of times shown in papers to be checked. Nutrition quality and other medical conditions. Additionally, the data set is relatively small with only 465 points versus millions of potential ones. We use a small one, so it was easier to manipulate. And also, this data is only from hospitals, so it doesn't count any home births or things like that. And that might trend it downwards in birth weight, is if you had a high risk baby, such as a low birth weight, which is very common, they would have to be delivered in a hospital versus at a birth center or a home birth, which would be screened for, especially at a 20-week ultrasound. So some things that we might want to consider to include to make the model more accurate will be including those ultrasound readings. So that would be head circumference, abdominal circumference, and femur length. There is quite a bit of error in some of those measurements. Some of the numbers I saw was 10 to 15%, but would definitely give you a much better expectation of what the final birth weight would be. So kind of in conclusion, the model that we used is a very simple tool that can be used for screening and might be used for mothers that might think they might have a low birth, that they might want to go get checked or monitored more often, or since gestational term was the biggest indicator, doctors can know with certainty that, if you have a baby at 35 weeks or less, term is the biggest factor, so it would be considered high risk, and they should plan for it. Same holds true if you had a 42, 43 week term baby, that would potentially be high risk for the mother with having, most likely a very large baby. So basically this model hopefully can be worked on further and then and refined and provide guidance to help, improve birth outcomes. So that concludes my presentation for multilinear regression. Thank you.